Welcome everyone to another CP Tap call. This is call number 166. And where is my thing? Here we go. Yeah, it's my pleasure to introduce today's speaker, Tom Brady. Tom has more than 14 years of experience designing, testing, and supporting automotive ADAS and infotainment applications using GMSL and other SerDes technologies. In his current role as a principal engineer, he supports the system design and architecture of video and control data connectivity within software-defined vehicles. Software-defined vehicles, never heard about that. So uh, today, Tom will present Time Hat applied to IEEE 1722 media clock phase recovery. So his work builds on the Time Appliances Project Time Hat platform using nanosecond level precision to achieve sub 100 nanosecond phase alignment of recovered media clock through the IEEE 1722 clock reference format. The project combines PTP4L and libAVTP with a high precision Grandmaster clock to synchronize two independent Raspberry Pis located at different hops in the Ethernet network. Tom will explore how nanosecond precision, hardware timestamping edges, and can be carried in CRF packets across network and used by local servos to control the clock recovery loop. In the spirit of Time Out project, the entire documentation uses off-the-shelf hardware showing what can be achieved when precision time is made practical and accessible. Thank you, Tom, for joining us. The floor is yours.
Thank you, Ahmad. And yes, so one of the big aspects of automotive connectivity today and some of the buzzwords is a software-defined vehicle, an SDV. And with that, there's all sorts of other software-defined networks inside cars and really kind of bridging and making the car updatable and controllable long after it's launched. And so one of the areas that we're looking to explore is, leveraging capabilities such as Ethernet, where you can really provide future flexibility with configurations as features change and you need, system upgrades. And so one of them is with the IEEE 1722 format. This allows bridging of all sorts of technologies. Today we're going to be focusing on the audio and video portion of it, Ethernet AVB, and showing how using a high precision clock based off of the Time Hat repo was able to achieve very good synchronization of my independent devices. All right, so I'm sure everyone's familiar with this device, but it really did inspire me along with some other videos from Ahmad and Jeff Geerling about leveraging this and making precision time available to people exploring this area and what it really unlocks. And so taking a page out of the book from this device, I wanted to learn more about the intricacies of precision time and how to leverage propagating that level of precision throughout a network, specifically a software-defined network like a car. And with cars starting to bridge and move that precision time, the PTP, into they're standardizing PTP for automotive as well. There's actually just a IEEE group working group 802.1DG looking for time-sensitive networking inside of cars. So a device like this and understanding the intricacies is really important to do. So from this, I took a lot of the aspects of this device and built my own. And the unique thing with an automotive environment is here, it's a lot more static and things are known, things aren't really changing as much. Yes, you may have a hot standby Grandmaster, but typically you do have one device disciplining the network coming from a GPS source. And so this was modified slightly to enable and configure emulate somewhat of a more zonal network in automotive architectures. So taking this and using this as my Grandmaster, it really allowed me to easily implement PTP for Linux and PHC to sys on top of the TS to PHC GPS repo. And so very easily, creating these running daemons, I'm able to synchronize the network off of my Grandmaster clock. So with that, there were some optimizations made for this network, such as not doing the best master clock algorithm because this is the best master clock. So turning off a lot of that discovery algorithm. Additionally, really wanted to push the consumer hardware as much as I could. So I ported it over to the Ubuntu real-time kernel. And what this allows me to do is actually isolate cores and pin cores for real-time processes and allow other procedures not to interrupt the running daemons, and we'll get into that later. And then another benefit is I dug in the I226, the Intel 226 from the time hat design. I wanted to make use of the high precision PTP hardware clock on there. So while that's being used for disciplining the hardware clock and the whole PTP network, I repurpose it as a high precision timestamping engine to bring that level of nanosecond accuracy to timestamping my hardware edges. So the goal of this is to recover audio and media clocks over a network. And so these are transported in two formats. The AAF format is the AVTP audio format, where it sends I2S audio over the network. And the CRF is the clock recovery format. And what that actually does is from my Grandmaster, I'm broadcasting the edges of my 48 kilohertz media clock. The really nice benefit of this, having both the Grandmaster be or having this device be both my Grandmaster and my talker, is everything is referencing the same time plane. So was able to accomplish very high precision with this, and yeah, it's a great device. So showing from a very high level what this architecture looks like, I just had a simple FPGA generating a 32-bit 1 kilohertz tone at 48 kilohertz sample rate. That is driving my Grandmaster. So the Grandmaster, like I said, has a dual role of both the Grandmaster and the talker. And from that, it's broadcasting out onto the network, the PTP for Linux synchronization, along with all of the other 1722 packet information for media clock recovery. To emulate somewhat more of a zonal network, I use some of our ADI industrial TSN switches. So the ADIN 3310, it's a 3-port TSN switch. And this allowed me to put my listeners at different hops within the network. But the hardware of these listeners is identical to the Grandmaster. So they're all making use of the high precision I226 PTP hardware clock, which you see there with kind of that feedback loop through the clock cleaner, along with synchronizing via PTP for Linux. So this is what was tested. The level of complexity can grow, but my bench is only so big, and this is already quite a handful of evaluation kits. But it did provide some great results. So this was just measuring. I'm just in my office here. I'm located right outside Metro Detroit. Got a pretty good view of the sky most days, and the precision of the Grandmaster based off of the time hat repo was really critical in being able to synchronize everything downstream. So this is just kind of a snapshot of my implementation, replicating what was done on the very nice form factor time hat on my CM4 board, and still achieved quite good results with majority of my time being under 15 nanoseconds. As you can see here, very high precision and disciplining of that PTP hardware clock. And what really this project benefits from is the precision of this Grandmaster being disciplined to this level of accuracy, because this is also the same clock that is being used for capturing all my audio media clock edges. This is then, once this is disciplined, I utilize PTP for Linux, and that allows me to propagate the precision through the network. And that is really, kind of step one of being able to benefit from that high precision clock. And so here I have PTP client 1, which is the one sharing the same TSN switch as my Grandmaster. And you can see, very good precision, pretty much sub 15 nanoseconds over an hour-long run. and then PTP client 2 just a little bit faster or slower. And obviously it's going through an additional hop, but just a few nanoseconds more. But you can see that the distribution of these clocks running over an hour gave very good precision in local disciplining of their oscillators. And that's what's critical for utilizing what was called Ethernet AVB is now called TSN. Everything's a little interchangeable, but the whole point of the 1722 is having disciplined local oscillators. So with this level of precision, just for a quick high-level overview of what this is and does, is when we're using Ethernet AVB or TSN, it's operating under the assumption that there is a disciplined local clock. And so the standard for this is 802.1 AS, which is based off of the PTP spec, but this is it's called general GPTP, which is a more generalized form of PTP precision. But with the whole network synchronized, I can now correlate events in time across the network because now all of my devices are talking in the same domain of time. The reason this is such a big benefit is with AVB TSN, there's the whole concept of presentation time or when to present a media sample to a buffer. So, even if you receive a audio sample, you don't play it right away. You wait until you are told by the packet when to present it to the buffer. And so in my setup where I have two different listeners at different locations of the network, one is just going to receive that packet before the other one. But with the presentation time, it's able to delay playback of that until the ABTP time is met in the packet. So this was originally used and has been used. I actually started my career at Harman, and this was one of the things created back then of transporting audio and video over a network, over an Ethernet network. But as it's evolved, a lot of other industries have seen the benefit of precision time. So you will now see not only AVB, but TSN or time-sensitive networking. They're kind of intermingled now in their explanations, but AVB is now a subset of TSN and time-sensitive networking. And there have been other uses, particularly in like industrial fields, that you can now have precise execution of commands and control. So not only are you having, controlled playback of audio and video, but you have command and control of actuation that can be executed precisely. Or in the event of you have a remote sensor, you can timestamp that acquired sample with that precision local time. So the whole effort of getting the grandmaster nice and disciplined and broadcast to the network allows everyone to talk at the same time base, regardless of where they are located within the car. So here's a few changes of what was done. It looks like a lot, but really it was
Um,
just, oh, yes.
Sorry for interrupting, but from the way you speak, it's like you think you're sharing, but you're not sharing. You're not sharing your screen because you'll
I
see
can see fine.
you'll yeah, you can see it. For some reason, I don't see it. Okay, from my
I see
side.
it well.
Okay.
Sorry, my bad.
Oh, no worries, no worries. So some of the changes from the original repo design was the main one was trying out the Ubuntu real-time kernel. This was just purely out of an effort to understand, pushing the Raspberry Pi hardware to its limit. And with this, if you create a Ubuntu account, you can have a handful of devices running this kernel and enable this preemptible capability. And really, the benefit of that is now I can isolate my cores to run uninterrupted my daemon. So I moved everything to cores 2 and 3, and that's where my real-time cores are configured for. So it did some kernel tuning. I have a link at the end that describes all this as well. But then that leaves core 0 and 1 for just general housekeeping of the Raspberry Pi device. So on core 2, that's where I put the TS to PHC, along with all my other devices needed for discipline of this network. And then I put the audio talker on its own core. And that's just because the level of traffic that it generates really didn't want it to be interrupted by any of the other processes. So really cool benefit to this. And this kind of helped more specifically with the audio generation, but a very cool capability of this to have a more deterministic operating system. And then on the bottom there, you'll see this is the other side benefit of this was inspired by the capability and the hard work of Ahmad's rework and driver fixes to the IGC driver. I was able to also leverage this for hardware timestamping of the I2S media clock edges, and that was a big benefit. So now both my PTP hardware clock is disciplined from the GPS, and it's sharing the same clock for capturing the edges of my media clock. So everything is talking in the same domain. And consequently, on my listener devices, they use a similar architecture where they also are able to use that SDP0 for a hardware timestamping. So if you zoom in a little bit, what you can see here is kind of my lower frequency but real-time processes on Core 2. So the discipline from the U-Blox GPS, and then I also have my PHC to sys disciplining the real-time clock or the clock of my operating system. And then the PTP Auto Grandmaster is running on there as well, and my CRF talker. So all of those are fairly low frequency, but the AAF talker, which is generating 48 kilohertz rate samples on the output, that's operating at a much faster rate. So pinning that to its own core allowed it to operate uninterrupted. A really nice benefit of this too is turning off all of the NTP or other time synchronization devices. Everything on my network is synchronized from this PTP for Linux daemon. So everything when I boot up is up to date, synchronized to GPS, and that is a huge benefit for this application. So I won't get into all these details, but this is really there's a great article from Ubuntu about tuning the real-time core, and this allows you to move things around and pin certain tasks to certain cores, along with moving around IRQs to make sure that any sort of interrupts won't interrupt my real-time tasks, but also allows my real-time tasks to preempt those other cores. So this is just kind of moving around some of the resources and making use of a more deterministic kernel operating system. And some of the other features are because I'm not really doing too much outside of broadcasting audio and time synchronization, I turned all the kind of performance throttlers off and just let everything run at max performance. And yeah, so this was kind of split between the command line running of this and also the command line.txt boot up script. So quite simple to implement and tune to your specific use case. So here is when I run the programs from the talker and the listener. You set the scheduling priority or the scheduling policy, and then you also pin it to the certain CPU core that you want. So here you can see I have on my talker, I have two processes running, one to broadcast the media clocks, and then the other to broadcast the captured I2S data from my FPGA implementation. And then on the listener, really tried to have mirroring looking scripts, so very similar, leveraging a lot of the features of the 1722. So the only other difference you'll see here is T, which is my presentation time. So that's saying pretty much and you'll see that this wasn't an issue, but if a media sample doesn't reach the destination within 500 microseconds, to drop that. And that is really where you can kind of contain and bound the latency of the packets on the network. So here's what it looks like to kind of go into the details of the 1722 packet format. So rather than sending 48 kilohertz edges onto the network, how the protocol works is per packet. So it sends, you can program and determine the rate at which you're broadcasting this onto the network. So I used all the default values of the spec, but every second I'm broadcasting at a 50 hertz rate. And each of those packets contains six clock recovery format edge timestamps. So here on the right, what you can see is on the top is my 48 kilohertz clock um, playing out. And then on the bottom is what I was calling the CRF control wave, so to speak. And so that's operating at a 300 hertz rate. So each of these CRF timestamps is 160 media clocks at that 48 kilohertz rate. The I226 can't sample at a 48 kilohertz rate. So what I simply did was just have my FPGA divide down to be edge aligned with the frame sync clock that I was outputting. And then you can see here on the right was where the GPS antenna is plugged in on SDP2. And then on SDP0, I'm using that to hardware timestamp my media clock edges. So once again, this is the dual benefit of them sharing one disciplining the clock and the other one taking advantage of the disciplined clock to broadcast that out onto the network with very high precision. And this is immediately evident when you start doing packet captures of this on the network. So using Wireshark, you can see here extremely precise 20 millisecond packet timing broadcast out onto the network. And so carrying this high precision, this is now, being broadcast at a very steady rate, being fed into my listener's servo, containing all of these high precision timestamps. And that's the coolest thing about this with, using the digital transport of this is I don't have to worry too much about, the drift of the whole network. I'm capturing those edges as the six timestamps, like I mentioned, from my talker. And so these are edge timestamp from my talker, very precise, put into the packet. So now everything downstream not only is synchronized to this clock, but it also has all of these hardware edges captured relative to that clock as well. So these timestamps are then fed into my listener's servo to servo the device as it does drift and is able to snap and keep those local clocks disciplined to the media clock source. So inside the 1722 format, you have all sorts of other fields, such as the stream ID, some other information like the frequency of the media clocks, which is 48 kilohertz, the multiplier of the pole, the timestamp interval. And so all of this allows you to calculate the rate at which you're generating these timestamps. So what I did on the bottom was just kind of show a conversion of all of these hardware edge timestamps. So these are coming from the Arctics out and captured on the I226 and then placed into the CRF packet to be broadcast downstream. And when you do a comparison, when you convert it into real time and then you do the comparison, you can see the level of accuracy at which I'm feeding all of the devices listening to this clock source on the network is very highly precise. So this was great and allowed all of my devices to be disciplined very tightly to that grandmaster, benefiting from all of that high precision discipline at the source. So how I used the control wave was the Raspberry Pi CM4 has a really nice PLL, hardware PLO. And with this is just some configuration, but essentially I'm generating a 300 hertz wave as my control wave. And then based on the timestamps that are broadcast to the network, I changed that fractional divider of the PLL to kind of move around and speed up or slow down the clock. So this control wave is what is used on my listeners. And when we go back to the block diagram, the control wave is also captured, hardware timestamp captured with the listener's I226's SDP pins. So it was just really nice having everything disciplined and having this great reference source for all of the devices on the network to look at in reference. Additionally, given that this is high performance audio and jitter and drops and pops and all of this is unacceptable, I added a clock cleaner on the output essentially. And so from Cirrus, they have the CS2600, which actually has an application note on automotive audio. And you can see the reference here is, it's being fed a wave and it's driving both the audio interface, which in my case is the Raspberry Pi, and then it's also driving the output codec. Um, so with this network, it's a great reference note of how to do this and how to recover clocks from the network. And then I was also another very good example of media clock recovery using 1722 on an FPGA. They also use the Cirrus clock cleaner, and that kind of cleans up the output, but it also has some other nice features to it for maintaining drops and discontinuities due to Ethernet packets. One of the nice things about the 1722 format is if you do drop a packet, it's not like the entire audio stream shuts down. It just waits until there's a trustworthy source to start servoing its local oscillator again. So here is just some configuration to give some information on what this is doing. So the CS2600 is taking in my 300 hertz control wave from my Raspberry Pi that's being generated. And it's multiplying it out into a 24.576, which is a standard audio media clock. And then it's divided down to the bit clock and the frame sync clock. So everything is now synchronized to that 300 hertz wave. On top of it, it has a auxiliary output that I use to buffer that 300 hertz wave and get a nice sharper rising edge going into the I226. So now this one device, it's a pretty small chip. The eval kit is big just because most eval kits are, but it's purely just for multiplying up that recovered 300 hertz wave and outputting it to the network. Additionally, there's a nice feature of this, which has a phase alignment, where if it does detect there's some drift, it will actually very quickly snap it back into alignment based on the threshold you sent. So devices like this are, being leveraged for very high performance audio, and used in these applications where you are recovering a clock from an Ethernet network. So what does that look like? Yeah, it's a bunch of wires, but essentially it's everything that I just talked about, where we have the 300 hertz wave that's coming in and then being buffered out. And you can see here on my I226 device, very similar architecture of capturing that 300 hertz wave, along with the clock being disciplined via PTP for Linux. And then these are just generating all my media clocks and my bit clocks as well. The device is really here. So it's a fairly small implementation. And ideally, I would like to kind of turn this into a board that could plug in and clean up a lot of this wiring. But regardless, here are some of the results of what this looks like on the network. So on the top, you can see my CRF talker with that 300 hertz control wave and the 48 kilohertz media clock underneath it. And then my listener, I believe this was the FAR listener, listener 2, being synchronized with its 300 hertz control wave to those CRF timestamps that I'm broadcasting on the network, and then the multiplied clock output that you can see there on the bottom. Here's a live demo, and let's see, I hope this. So here at the top, you can see that is my media clock from the FPGA, and then on the bottom, you can see the two media clocks that are recovered and then fed through the clock multiplier of the Cirrus part, and you can see how nice and precisely synchronized they are to each other, even at different hops of the network. So with this allows me to, broadcast audio to two devices that are separated within a network, leveraging the capability of presentation time, which is based off of that PTP synchronization driven from my Grandmaster. So really great output of 100 nanosecond just about synchronization between these two across an Ethernet network. So here's just some other additional results, kind of going back to the block diagram. So the latency, which is another big factor of this, broadcast across the network was about 100 microseconds, which was quite good for audio streaming across a network across 2 hops. The jitter, the really nice thing about this is any jitter in my Grandmaster or in my media clock source, the rest of the devices also follow that. So, it's very tight, very low jitter on my resulting clock. And then the synchronization between the two is on average about 50 nanoseconds. So here, just kind of going back to the block diagram, very, mirroring some of that Cirrus application note and that IEEE paper is taking that control wave out that's recovered from those CRF packets, using that buffered output to capture and compare the two, servo the clock, and then drive both the Raspberry Pi CM4 and then whatever downstream audio codec that is connected to it as well. Additionally, took this into the office and just wanted to verify with an audio precision that it is interoperable, outside of my little bench setup. So here we used an audio precision to generate to be my I2S source, generating 32K audio out into the Grandmaster. And then on my farthest listener, I have my I2S sync. And so here, it is digital audio, but you can see very low jitter. And as a result of that, very low THD plus noise on my audio output, along with a very flat frequency response. So what we would expect, but also, it's good to actually test it on devices like the Audio Precision, which are used in a lot of audio applications for benchmarking and qualification of audio fidelity. So in conclusion, this really was a great example of being able to leverage high precision timekeeping for my specific application, which required a synchronized network for media clock recovery. This allowed me to transport an audio clock across a network of varying hops to not only recover it with high fidelity, but with low jitter, to have devices synchronized, all kind of that's just in the background with that Grandmaster clock synchronizing all these local devices. The other goal was to kind of push this as far as you could with commercially available devices and things. So that's another inspiration behind that, because this precision stuff can get very expensive, but definitely wanted to continue making things like this available to people and try to leverage it in their own applications. So building off of the great repo of TimeHat, I did open source the automotive TimeHat device. It's just a handful of daemons that you can run and get PTP for Linux, synchronizing your devices, along with PHC assist to synchronize your local clocks. And then with that, handle it however you would like, whatever type of application you have. And a lot of great resources. So this is something that, inspired. Like any good engineer, you stumble upon a Jeff Geerling video and got to see Amabagawi and his presentation on the time card. So great explanations of that and making something that complex approachable, along with the open source Avenue Alliance for libAVTP, which is what I used for the CRF and AAF transport, Linux PTP project. The TSN documentation from Intel gives a great overview of how to kind of bring all of these pieces together, leveraging that Avenue library, and then a very good article from Ubuntu about tuning that real-time core. So that's really where I got into the details of that and understanding the capabilities of tuning my Linux kernel. So with that, just also want to call out my other ADI colleagues, Brent and Brandon and Jeremy, for helping me with my questions and all the measurements. But really, it's a fun and fascinating time to be part of high precision timekeeping and great learning experience. So thank you to the whole community.
Excellent. Thank you very much, Tom. One more thing, maybe you can add to the list, which is related to the TimeHat, is this repo that I just added there.
Okay.
So basically, the NVM flashing for Intel was for a long time stuck to x86, but I was able to push it to now be also available to Raspberry Pi. So now you can compile it on Raspberry Pi and then add a lot of features to it. Like, for example, it can give you a random generated legal the MAC address. So
Okay.
like basically it will not go over the reserved ones, and it will just randomly pick, like, give you things and program it and so on. So the flashing doesn't need no longer needs x86. Now you can just do it directly on Raspberry Pi.
Cool. No, thank you very much. Yeah, it's little things like this and that other the fix to the IGC driver. It really helps leveraging this device. So thank you very much. I'll
You're
include
very
that.
well. All right, let's open the floor for questions. There was some comments or questions in the chat.
Oh yeah. So yeah, Bogdan asked about a source of discipline when GPS is absent, and that's definitely one. Like I said, kind of the hot standby GPS or what specifically kind of that holdover in those implementations. For me in automotive right now, that's an actively discussed question of if you do lose that level of precision, what can you fall back on? And so every customer kind of has their own implementation of that. But that's kind of the nice thing, as I mentioned with this 1722 protocol, is if it does lose a clock, there's bits that it can indicate that it's the media clock it's uncertain about, or there's been a media clock reset. So there are things baked into the protocol to alert the system of that. But yeah, when GPS is absent, that is definitely something that there are other less precise things you can fall back on, but every customer kind of implements it a little differently from what I've seen.
Paul is putting something.
Yeah, so I opted not to steer the 2600. This was purely just using it as a clock multiplier. I was trying to look at leveraging the whole control loop inside the Raspberry Pi and kind of basing it off of the Linux PTP uh, servo algorithms and leveraging all of that and feeding back those captured timestamps. That was another approach that I also explored, but I just chose to leverage keeping the control in the Raspberry Pi and having this CS2600 as cleaning up the clock on the output.
Bob, do you have anything?
Yes. Thanks, Tom and Ahmad. A couple times, Tom, you mentioned that there were IGC driver fixes that helped. I've had some personal scar tissue accumulate from IGC driver bugs. Could you recap where you got the current best IGC driver, please?
The guy running the call, he helped
Yeah.
with some of the,
Okay.
there was some issues with the driver not, it was capturing both the rising and falling edge, and just, I didn't need both rising and falling. And so modified some of the IGC drivers to just capture that, some small tweaks to it. But really that helped a lot because it completely threw off my whole PTP algorithm when it was capturing both those edges. It was
Yeah.
railing back and forth. So in the TimeHat repo that's there are the IGC driver fixes that are great
Okay.
references.
All right, thanks. Yeah, I've also run into rate, as you try and scale up, say, to multiple PTP packets per second, dozens, if you're really trying to get the accuracy down, then the guy receiving all those packets has some scaling issues in the driver and I think it's even a hardware issue underneath that I bumped into. I hope you don't run into that as you
No, I
scale up.
definitely, like, as I was messing around with some of those features, I noticed some oddities. So I tried to leave as much default as possible. But yeah, I did encounter that as well. And it would be nice if
It'll,
that driver was fixed because these are, I think, fairly simple fixes from, what I saw. So hopefully, we can get some patches to that.
No, I'm
okay.
actually putting some bandwidth to actually mainline it, put it
Oh,
upstream.
excellent.
Thank you. Thank
Thank
you.
you.
Applause. All right.
So there is another funny one, and that is there is a I forgot right now. There is a TI ARM that has PTM, and then when you use this hat on that one, I mean, the hat doesn't match. What matches is that the IPC connect, like the what do you call, the flat cable.
Yeah, yeah.
And when you plug it there, you still don't see PTM. And then you wonder why. If you go dig deep in IGC driver, you see like it first checks, is it an Intel processor before it checks it has PTM or not? So like that's, again, I'm trying to work on that to mainline, like upstream it as well to like I mean, there, if you don't work on these things, and or like basically just fix them local, after a while they just disappear. So
Yeah,
it's always a good practice, but oh boy,
yeah.
upstreaming something. I'm literally in the middle of one little thing for the time card to enable the LEDs, and it's pain. I mean, it's beautiful how it actually works. So many people, you need to get consensus from so many people
Yeah,
to go through something. And eventually when it lands, it's owned by everyone because everyone has to maintain it. I mean, in that pod, and then
yes.
sometimes you get that delegated to another group. Like for example, that was from the net, and now I'm getting pushed to the whole LED group because these are LEDs, even though on the time card driver. So, and then it's very interesting. It's very interesting. Yeah.
Yeah, and it's a great feature having that software-defined pin and capturing that, and so
Yeah.
being able to kind of dual purpose it. But I did run into some other funky things trying to capture it from two devices. So it seemed like,
Wonderful.
yeah,
Wonderful. And I'm very excited about all these like analog device chips that they can now take this and further do things with audio, because we did actually a demo 2 years ago in OCP uh, without, of course, this chip or anything. What we did is we basically had two MP3 players, like
hmm
in software, and then we were using NTP and then later PTP, and then we're playing back two sounds, because like it's very interesting, like or phase measurement from between they call it binaural sensing. Like
yeah.
basically you can find where the sound comes from. You can actually go in like kilohertz and a little bit further, if not like, I mean, tens of kilohertz, so, on phase measurement. So if you play back the two sounds and then you align them with NTP, you can see like, okay, I want to have the sound coming from front, but no, it's not like drifting away. But when you do PTP, you can actually lock it to front, and then you can make it then spin around like very clean. So
Oh, that's cool.
yeah, that's very interesting. Like, I mean, because I really thought a lot, like, how can I sense something in like, in kilohertz and above to make it look really like differentiate between PTP and NT. I mean, that's like one of the biggest things for like the audio streaming. Like you have all these speakers in a stadium to all like phase align to basically give the best experience to people. And then now this hardware, instead of like we use a NUC to do the whole thing. Now you can just skip all of that and just
Yeah.
do a chip. Yeah.
Yeah, and one of the applications that we do in some of our other chips, our A to B chips, is active noise cancellation. So you're
Yeah.
sensing a
Yeah.
mic and then you're canceling it out, and so that was
Yeah.
another,
ANC. Yeah.
yes, ANC. So a lot of very interesting application for synchronized audio.
It's beautiful. Yeah. All right. Any more questions? There was actually another one, like you brought it up. It's like basically in a hospital, you have a hospital, you have a highway, and in between that, I mean, you have like this whole whatever yard or whatever. You can put microphones there closer to the highway, and
hmm
then like have it all. Everything has to be synchronized, and then in the hospital, in like in the rooms in front, like facing the like in a hospital facing the highway, you have like those speakers that they need to do the ANC, but
hmm
you need everything time to know, okay, this wave is propagating now. I will hit it exactly at the
Yeah,
right time.
exactly.
It just sets the context.
All right, Paul.
Sorry, I'm at Salomar right now with a broken arm, so
Oh
typing
goodness.
with one finger is a bit slower. So, Tom, one thing I noticed on slide 17, you're routing the buffered 300 hertz into SPD0, which is one of the I226's timestamp pins. So each listener can already measure its own media clock against the PTP hardware clock. the measurement is there, but the scope trace shows that there's two listeners about 150 nanoseconds apart, and that's roughly your 8 clock alignment threshold. So the offset is being measured and not corrected. Is there a reason the loop isn't closed? There's no control path back to the CS2600, or a deliberate choice?
Yeah, so the CS2600 is purely being used as the clock multiplier. I was starting to mess around with controlling it with I squared C and kind of creating its own driver to modulate that. But before I had the CS2600, I had my architecture leveraging that control wave with the PLL, the hardware PLL from the Raspberry Pi. And so that is kind of what I started with, and that was where a lot of the software was developed around. But so it does, the Raspberry Pi does take that buffered output and slew itself based on leveraging that cleaned output. But yeah, another alternative approach would be definitely controlling that CS2600 directly.
So that sounds like a silicon roadmap gap, and which is one of the things I'm investigating. And I think that what you're saying here is that it's good enough for audio, and that's fine, and it's true. So does it stay good enough when this hardware is used for something that isn't audio?
That's a good question. So yeah, so that's like I mentioned, the IEEE 1722 format is being used for all sorts of other I2C, UART, SPI, control interfaces, PWM interfaces. And so this is one application of it. They all use PTP time level accuracy for acquisition. And so in terms of kind of disciplining that local clock, it's a good question of how that could be handled for those other interfaces. They're not as critical as the accuracy that audio needs and the drift of the phase. But being able to be synchronized and even nanosecond precision is kind of overkill for command and control applications. So the PTP alignment alone is pretty tight to actuate and capture those timestamped events or trigger those events.
Thank you.
Yes.
All right. Any more questions?
Yeah, can you please, Tom, put your email address on the chat?
Oh, sure. Yes.
Or
Because
just update, Tom, update the
I
slides,
have,
then add it there so then people can get it.
I have
Because
few
the chat
questions.
doesn't go in the record.
I will send them to you via email and copy the whole OCB tab.
Okay, yeah, absolutely. Yeah, I'll put it in the chat and then I'll also put it in the
Yeah,
presentation.
I will. Once you give me the email, I type them down. I will send the email to you.
Okay, thank you.
Any more questions?
Yeah, this is Bogdan. I have a question.
Good.
Where are the slides? Over?
The slides will get published with the recording on the wiki, which just go timeappliances.com. And I think there is some maintenance that will go until August 31st. And basically everything is frozen until there, but I will post it anyways. And if it gets lost, I'll post it again. So that's how we do it, right?
Thank you. And
You're
I have one more comment. This is Bogdan again. I'm recording the events from an event-based camera together with frames.
Yeah.
And this is very important for me to timestamp those events. They come up to 10 million samples per second. This is the maximum. They're asynchronous. That's another application. Over.
Wonderful. All right.
Presentation. Thank you.
You're welcome. Hisham, anything else?
No, thank you very much.
Okay, all good. Perfect. Okay, so if no more questions, again, thank you very much, Tom.
Yep, thank you.
And we'll see everyone in 2 weeks by a presentation from Okto Halsima about a simplified approach for a grandmaster. It's all related. We're going very hardware recently. All right. Bye, everyone.
All right, thank you.
You're welcome.